All right, so if you liked last week, then you're going to love this week because it's basically more of the same thing. Last week, we talked about doing inference for proportions. We looked at one proportion and two proportions. When we're talking about proportions, then our response variable is categorical. And this week, we're going to start talking about means. And when we do inference for means, the response variable is quantitative. So that's one good way to tell the difference between whether you're working with means or whether you're working with proportions. When we want to do inference for the population mean, then we need to know about the distribution of the sampling mean, or in other words, the sampling distribution for X bar. And if you recall, the central limit theorem said that if we take samples that are large, then the distribution of many common sample statistics can be approximated with a normal distribution. And that certainly applies to X bar. So if we have a large enough sample size, then the sampling distribution for X bar is also going to be normally distributed. And the larger your sample size, the more normal the distribution of X bar is going to be. So here's just some pictures that are going to kind of show us how that central limit theorem works when we're talking about a mean. So over here on the left, we have a population distribution. And you can see that this, so when we talk about the population distribution, we're talking about essentially doing a graph of all the individuals in the population. And you can see by this graph that it's definitely skewed. It's skewed to the right. So this is not a beautiful symmetric bell-shaped distribution. And if we take samples of size 10 from that population, here's one possible sample data distribution that we could get, which you can see is skewed just like the population. And if we take lots and lots of samples of size 10, and from each of those samples, we compute the sample mean, and then we do a graph of the sample means, then it might look something like this, which you can tell is still a little bit skewed, but definitely not as skewed as the original population. Now, if we take samples of size 30, so here's an example of what one sample of size 30 would look like, the distribution of individuals from one sample. And if we take lots and lots of samples, all of size 30, from each of those samples, we calculate our sample mean X bar, and then we do a graph of all those X bar values, then it would look something like this. So now we can see that this is really starting to look more like a bell-shaped symmetric distribution. It does seem like maybe it's just slightly, ever so slightly still skewed, but definitely less skewed than when we took samples of size 10 and a lot less skewed than our original population. And if we do that same thing, only now we take a sample of size 50, then here's what our, one sample of size 50 is going to be skewed. And if we look at sample means from lots of samples of size 50, and we graph those sample means, so in other words, the sampling distribution for X bar, then you can see that it now follows that beautiful bell-shaped curve that we all love. So notice though here that the distribution of the data in a particular sample is always going to follow the same basic shape as the population. So if I graph the individuals in a sample, the shape should match the population shape. So the key idea here, or one of the key ideas, is to keep in mind that distribution of sample data is different than the distribution of sample means. So when we talk about the sampling distribution, that is different than the distribution of the sample data, which can be really tricky because they sound so incredibly similar, but they're totally different things, and it's really important to remember that. And when we're doing inference, so in other words, when we're doing confidence intervals and hypothesis tests, for the population mean, then the one that we really care about is the distribution of the sample mean. So in other words, the sampling distribution. And we can see here that as long as our sample size is big enough, kind of didn't matter that our original population was all skewed and wonky. Our sampling distribution is going to be approximately normal. And since that's what we use to come up with our p-values, that's what we use to come up with our margin of error in a confidence interval, then we can use the normal distribution as a model to approximate the sampling distribution. So when we use the normal distribution to approximate the sampling distribution for X bar, then the standard error for X bar can be calculated using this formula, just sigma divided by the square root of n. Remember, sigma is our population standard deviation. And you can tell from this formula here that the larger our sample size is, then the smaller the standard error is going to be, okay, which makes sense. And remember, when we originally started talking about sampling distributions, we said, hey, the bigger your sample size, the smaller the standard error. So there's a bunch of different terms that we throw out that all sound really similar to each other. So I want to make sure that you really understand the difference between the different terms. So we're going to do a little quickie poll here and see how well you do. Okay, so I'm gonna launch the polling feature here in Zoom. So when we're talking about the standard deviation of the population, which one of those three symbols would be the standard deviation of the population? All right, good. It looks like most of you got it right. So when we're talking about the population standard deviation, so the standard deviation among all the individuals in the population, then we're talking about sigma. Okay, next one. What about when we're talking about the standard deviation of our sample? Which one is going to represent the standard deviation of the sample? All right, so most people got this right, but it was a little bit closer this time. When we're talking about the standard deviation of the sample, so in other words, the standard deviation among individuals in the sample, then we use S. So S is the standard deviation of the sample. And finally, the last one, if we talk about the standard deviation of the sample mean, which one is going to be the standard deviation of the sample mean? All right, good. We got really, really close to 100% on this one. So the correct answer is C. C is going to be the standard deviation of the sample mean. Okay, so they do sound super close to each other. Standard deviation of the sample, standard deviation of the sample mean, even standard deviation of the population. So it's really important that you know what we're talking about and realize that they are distinctly different from each other. All right, so we said that the standard error when we're working with one mean is going to be equal to sigma over the square root of n. But as we just discussed, sigma is the population standard deviation. So in practice, then we most of the time don't know what the population standard deviation is. So instead, we're going to have to use something from our sample to estimate what that population standard deviation is. And we know that the best estimate for a parameter is the sample statistic. So if our parameter is sigma, then our sample statistic, our best estimate, would be S. So we can use S to estimate sigma in order to find the standard error of our sampling distribution. However, if we use S to estimate sigma, then it changes things a little bit, okay? Because now, instead of just estimating the mean from our sample, we're estimating the mean and the standard deviation. So we're estimating more things, and the more things that you estimate, then it adds a little bit more uncertainty in the whole thing. And if there's a little bit more uncertainty, that adds a little bit more variation. So when we use S to replace sigma, then the resulting distribution is no longer a normal distribution. Instead, it's something called a t distribution. So we're going to write down a bunch of things about the t distribution, and then we're going to look a little bit more about what the t distribution is and how we're going to use the t distribution. All right, so first of all, we said, okay, if sigma is known, then the normal distribution is a good approximation for the distribution of the test statistic in a test of one mean. So if sigma, so sigma was that little circle curly thing. If sigma is known, the normal distribution is a good approximation for the distribution of the test statistic. So the normal distribution is a good approximation for the distribution of the test statistic for a test of one mean. So if we know sigma, then the resulting distribution that we're going to use is the normal distribution. Everything is great. But like I said, in real life, we actually rarely know what sigma is without also knowing what mu is. So most of the time in real life, we're going to have to use S to estimate sigma. So if sigma is unknown, then replacing sigma with S changes the distribution of the test statistic from a normal distribution to a t distribution. So if sigma is unknown, replacing sigma with S changes the distribution of the test statistic from normal to a t distribution. And it's always a lowercase t. So t distributions, they are very, very similar to normal distributions. They're still bell-shaped, they're symmetric, they're single-peaked. The main difference is that t distributions are going to be a little bit flatter and a little bit more spread out, meaning that there's going to be more area in the tails. That represents the extra uncertainty that we have by estimating more things. So let me write that down first. So I have t distributions are similar to normal distributions. So they're similar. In other words, they're going to be symmetric, single-peaked, bell-shaped. Okay, but they're going to be flatter and a little bit more spread out than the normal distribution. All right, so there's actually multiple t distributions, and a particular t distribution is characterized by something called its degrees of freedom. So a particular t distribution is going to be characterized by its degrees of freedom. And degrees of freedom is just a measure of how much information that we have in the sample, and it's always going to be related to the sample size. And we also usually abbreviate degrees of freedom by just calling it DF. So I'll just say degrees of freedom is related to sample size. So the higher the sample size, the higher the degrees of freedom. When we talk about notation for a t distribution, then we use t, and then in parentheses, we put the number of degrees of freedom. And I'm not really sure why your book doesn't just put df in that little thing, but it's always done like t in parentheses k, and k is equal to the number of degrees of freedom. So to be consistent with your book, that's how I'm doing it too. And the larger your degrees of freedom, so in other words, the larger your sample size, the closer your t distribution is going to look to a normal distribution. So the higher the degrees of freedom, the closer the t distribution is to the normal distribution. Let's look at some pictures of some t distributions with the normal distribution here. So the black line is the standard normal distribution. So it's just a regular normal distribution. And then we have two different t distributions that you can see here for comparison. So the red dashed line here is a t distribution with 5 degrees of freedom. And the blue dashed line is a t distribution with 15 degrees of freedom. So you can see from here that the more degrees of freedom you have, the closer that t distribution gets to looking like a normal distribution. And you can also see how in the t distribution, there's a little bit more area out here in the tail. So it's a little flatter in the center, a little higher on the edges. So remember, when we're doing things like finding p-values, we're looking for the area in the tail. So when we have a t distribution, we're going to have a bigger amount of area in the tail for the same like test statistic value as we would in a normal distribution. So we're going to get a little bit larger p-values, and our confidence intervals are going to be a little bit wider when using the t-distribution. Again, just to reflect that extra uncertainty we have because we're estimating more things. Now, as far as actually using a t-distribution, it's going to be very, very similar to when we use the normal distribution. The only real difference, as far as we're concerned, because we're still going to use stat key and stuff like that, is that we're going to have to be aware of how many degrees of freedom that we have, and we're going to have to input that into stat key as well. Okay, question from the chat window. Is there a degrees of freedom number that is equal to a normal distribution? There's not one that's like, that we're like, oh, once it hits this, it's equal per se, but definitely like once you get up to like 1,000 degrees of freedom, they're essentially the same. Even 100 degrees of freedom is getting pretty darn close. So in case you're wondering where the t-distribution came from, the t-distribution was, I don't know, like, are distributions, like, are they discovered? Are they invented? I'm not sure exactly. But there is this guy, his name was Gosset, and he was the head brewmaster at Guinness Breweries back in the day. And he, I guess, was doing statistics in secret on the side. And he kind of, in his work, he kind of discovered that when we use S to replace sigma, things weren't exactly following a normal distribution anymore. So he invented, I don't know if it's invented, like I said, I'm not sure exactly what the right terminology is, but he discovered, invented, came up with the t-distributions. So that's where they came from. But he didn't want anybody to know that he was secretly doing statistics because they might think he was a nerd. So he published under the pseudonym of Student T, and that's how the t-distribution became known as the t-distribution. All right, so let's talk about how we're actually going to use this stuff in an actual problem. And so first we're going to talk about how to do a confidence interval, and then we're going to talk about how to do a hypothesis test. So for a confidence interval, remember that the general formula for a confidence interval in last week anyway was a statistic plus or minus z star times the standard error. But z star comes from a normal distribution. It's a normal distribution critical value. And when we replace sigma with S, now we're going to have to use the t-distribution. So can anybody guess what we're going to do here? Instead of using Z star, what do you think we're going to use? So Z star is out, and now we're going to use T star. Exactly. So we're going to use T star instead of Z star. And T star is still a critical value, but this time it's going to be a critical value from the T distribution. And remember, Z star was based on our level of confidence. T star is also based on our level of confidence. And in addition, it's based on the number of degrees of freedom that we have. So once we replace T star, Z star with T star, then here's what our resulting confidence interval formula looks like. So we're going to have X bar plus and minus T star times S over the square root of N. That's how we're going to compute our confidence interval. And the degrees of freedom for T star are going to be equal to N minus 1. So N is our sample size. So just the number of in our sample minus 1. All right, let's talk about the conditions for being able to use this t-distribution approximation to our sampling distribution. And we have two conditions. The first one is that we have a simple random sample. And when you're actually conducting an experiment, this is a really important one, and you as the experimenter or researcher need to be aware of the methods that you're using to collect the sample. Now in our class, we're always analyzing other people's data, so we're not going to focus as much on this simple random sample condition. If they don't say anything in the problem that would make us believe that it's not a simple random sample, then we would be concerned. But otherwise, we're just kind of going to go on the assumption that they used a good sampling method. The one that we're really going to focus on in our class is the second condition. So here's kind of a little background on the second condition. So when we use the t-distribution, it requires that the data comes from a normal distribution. And this assumption is about the population data, not the distribution of the sample statistic. But when we have really large sample sizes, then we don't have to worry about that as much because S is going to be a very good estimate of sigma and T is going to be very close to the normal distribution. So kind of the bottom line is that if our sample size is large, then it doesn't really matter what our population looks like. But if our sample size is smaller, then we only want to use the T distribution if our population is approximately normally distributed. So one problem with this is that the way that we're going to check this is we're going to graph our sample data. And if we have a really small sample size, it might be really tricky to tell if the data came from a normal distribution or not. So here's a population that's obviously not normal. And here's 3 different samples that came from that population. Okay, and they all look kind of wonky. But again, it's a little bit hard to tell because here's a normal population, and if we're taking multiple samples from a normal population, you can see that some of them look great, but this middle one looks a little bit skewed. So even though it came from a normal distribution, it still looks a little bit skewed. So so it can be tricky to tell from just looking at our sample data when the sample data is small whether or not the population was normally distributed. So we're going to do our best. Okay, we're going to have kind of a rule of thumb. So we're basically, if the sample sizes are small, we're going to use the T distribution. If the data look reasonably symmetric and do not have any extreme outliers, and then of course remember that it's an approximation in the end of the day anyway. And in real life, if you have small sample sizes, then it might be a better idea to use simulation methods to come up with your confidence intervals and hypothesis tests rather than using the theoretical distributions like we're doing here in chapter 6. So maybe you'd rather do bootstrapping and randomization because those do not have the same requirements that these tests in chapter 6 have. Okay, so going back to our conditions for our confidence interval. So simple random sample is the first one. The second one is that the population is approximately normal or our sample size is large. Okay, and we're going to check, the way that we check to see if the population is approximately normal is by doing a graph of the sample data and looking at the shape of the sample data. Okay, and we're looking at one quantitative variable here. So who remembers what a good graph to look at the distribution of one quantitative variable would be? Okay, a dot plot would be a great choice. What's another one? Histogram. Yeah, dot plot and histogram are going to be the best at figuring out the shape. If you're in a pickle, you know, a box plot could work in a pinch as far as figuring out symmetric versus not symmetric or outliers. But a histogram and a dot plot are going to be the best choices. So in order to check to see if the population is normal, we can graph the sample data because the sample data should be like a mini population. It should reflect the shape of the population. So we're going to do a histogram or dot plot of our sample data. Okay, and as long as it's reasonably symmetric with no extreme outliers, then we're going to say it's okay that we meet the condition. So if it is reasonably symmetric with no extreme outliers, oops, that's supposed to say outliers, then we meet this condition. All right, and remember that this is an either or thing. So we need the population to be approximately normal or our sample size is large. So if we do the histogram and we're like, oh man, there's outliers, that's bad. But our sample size is like 50, then we're like, hey, no problem. I only have to have one of these things be true in order for me to meet the conditions altogether, okay? So the graph is going to be especially important when we have a small sample size. All right, so let's talk about T star in our formula here. and how we're going to find that T star. And like I said before, it's very, very similar to how we found Z star. The main difference is that now we also have to worry about degrees of freedom. So to do this, we're going to go to stat key. All right, so here in stat key, we're going to come down to theoretical distributions, and this time we're going to choose T. And the first thing it's going to ask us when we click on the T distribution is it's going to ask us for our degrees of freedom. So we're going to make one up here that we're going to look at. Let's say that we're looking at, we collected a sample, and our sample had 58 people in it. Okay, so we took a sample of size 58. So if my sample size is 58, how many degrees of freedom would I have? Yeah, remember degrees of freedom is just equal to n minus 1 for this this section. So we would have 57 degrees of freedom. So I would type in 57 right here in the degrees of freedom section. So I'll write down what we're doing here now that I'm in here over on the side. So in my hypothetical example here, n was equal to 58. That means that my degrees of freedom, which is equal to n minus 1, was equal to 57. And my confidence level that I want, I want to be 90% confident today. All right, so once I'm in, and notice that over here under the parameters, then it has our degrees of freedom that we entered in. Then finding the T star is the same as we did to find Z star. So we're going to click on to tail. We change the number in the center box to be the same as our confidence level. So I'm changing that to be 0.90. And then this bottom box here is going to be my T star. So this center box here, that's my confidence level. And then that makes this bottom box here my T star value. So that's the number that I would use if I was constructing a confidence interval. All right, I'm going to let you guys practice seeing if you can find T star for a few different values here. So I'm going to go back to my presentation because that's where I have them listed. If you printed out the note sheets for today, they're on there as well. Okay, so there's these 3 different scenarios here. So practice using stat key to see if you can find the appropriate T star for each one of those different scenarios. All right, looks like we've got a lot of people done here. So let's look at these really fast. We'll see what we got. So the first one says confidence level of 95% and 30 degrees of freedom. So if I change my degrees of freedom over here to 30, and then I click on to tail, 95% is what I want. So 2.042 would be the T star for that first one. For the second one, it says I have 16 degrees of freedom and that I want to be 99% confident. So I put 0.99 in that center box, and that gives me a T star of 2.921. And then for my last one, I have 47 degrees of freedom, and I want to be 90% confident. So I end up with 1.678. Okay, so notice that when we're finding T star, it only is based on 2 things. It's based on degrees of freedom, and it's based on the confidence level. Okay, notice that there is no formula to calculate T star. It's just a value from the T distribution that you get by knowing confidence level and degrees of freedom. All right, looks like we did pretty good overall. About 3/4 of the class got all 3 of those answers right, and about 1/4 of the class missed some. So if you have questions on how to do that, definitely hang on at the end of class and ask me. I'd be happy to walk through that a little bit slower so that you can figure out how to do those. On the exam, on this exam, you are going to be able to access stat key during the exam. So I'm going to have a link to stat key inside the exam, and I'm going to give you permission to be able to go to stat key during the exam. So you can find your T star using stat key on the exam. However, sometimes it's easier for T star to use a table instead of using stat key. Kind of like for Z star, remember once we found those 3 values, it's like, hey, those are the ones we're only ever going to need. If I just use this table, or if I have them written down somewhere, then I don't have to do it every time. Similar idea, I guess, to with the T star. So what I'm going to do on the test for T star, if you're interested, like I said, you can totally use stat key if you like that. But if you would like, I will allow you to have a printout of the critical values paper, I guess, table. Let me show you what it looks like. So there's a couple of ways you can get this. And one of those is if you look in the resources, so this was the same folder that was in week 11. Now I put it in week 12 here as well. And inside this folder, there's the standard error calculator, which I'm sure you became best friends with over the weekend. It also has this chapter 6 formula page, which you will be allowed to have a printout of this chapter 6 formula page with you on the exam. So that's another thing. You can have 2 printouts on the exam. You can have the chapter 6 formulas, and you can have this down here where it says critical values for confidence intervals. And this, just since the most common confidence levels are 90, 95, and 99, this just gives a whole bunch of different degrees of freedom and their corresponding level of confidence here. So for example, the first one that we just did had 30 degrees of freedom and 95% confident. So I'd come down here to 30 degrees of freedom and 95% confident, and you can see it's 2.042. Okay, so same thing that we got using the applet, not the applet. Yeah, then what's it called? Using stat key. Same thing we got using stat key. All right, the second one was 99% confident and 16 degrees of freedom. So here's 16 degrees of freedom. Come over here to 99% confident, 2.921. So you can see same answer that we got. Once the degrees of freedom start getting really big, the numbers are so similar to each other that we kind of group them together here in our table. And look here, according to this table, once you hit 200 degrees of freedom, then you're close enough to the normal distribution to just use that instead. So our third one had 47 degrees of freedom, and we were looking at 90% confident. So this would say 1.679, and the value that we got when we put in the exact number of degrees of freedom, we got 1.678. So you can see that they're only off by a really small number there. So it's close enough that you should be able to use it. So this is an option. If you want to print this out, use it in your homework, use it on the exam, then a lot of people like that better than having to use stat key all the time. All right, so let's look at an example here. So this is some data that was collected by some of my students. I teach another version of this class for another university, and at that university they require that all the students do a project. So they do a group project where they have to collect data and then analyzing it using all the tools that they learn in our class. So it's kind of fun. And one of my groups, it's an online class, so I get people from all over the world, and not as many international people. I usually have like a couple international people each semester, mostly just all over the country though. So one group wanted to find out how many fries were in a medium order of French fries at McDonald's. And so all the students in the group that were living all across the country, they purchased 30 medium fries at McDonald's restaurants across the country. And the mean number of fries in their sample was 70 with a standard deviation of 12.4. And we want to give a 90% confidence interval for the mean number of fries in a medium order of French fries at McDonald's. So first thing that we want to do is define our parameter. And when we are talking about doing inference for one mean, then what should be the parameter? What would be the symbol for the parameter? So I'm doing inference for one mean. What symbol should I use for my parameter? Mu, exactly. Okay, and mu is a mean, so mu equals the mean and then whatever we measured. So mean number of fries in a medium order at McDonald's. So mean number of fries in a medium order from McDonald's. All right, next up, we're going to compute our sample statistic, or if it's already computed for it, we can just identify it with, of course, the correct notation. So what notation should we use for the sample statistic for this problem? If my parameter was mu, that means my sample statistic is X bar, exactly. So we have X bar, and they didn't actually give us the data. They just already told us that the mean number of fries in their sample was 70. So X bar is equal to 70. All right, the next thing that we need to do is check our conditions. Okay, so the conditions, the main condition that we're worried about is we want either the data to be normal or and be large enough. Okay, so if we look at a graph from their data, and this time I only have a box plot of their data, but looking at this box plot, does it look like the data is reasonably symmetric with no outliers? Yeah, it does based on this box plot, right? We can't get the full on shape from a box plot, but definitely we can tell that it looks reasonably symmetric and that there's no outliers. So, so the data being normal, we meet that condition. And in addition, then our sample size was at least 30. So we meet the conditions that way as well. Okay, remember only one of these things has to be true though. If both of them are true, then it's like an extra bonus. So in this case, double bonus for us. Okay, so we do meet the conditions. So now we're ready to go ahead and construct our confidence interval. So here is the formula for our confidence interval. And I've already got X bar, S, and N figured out here. So I need to figure out my T star. So remember, T star is based on two things. It's based on my confidence level, and it's based on my degrees of freedom. So for my confidence level, how confident did I want to be? Okay, I think I wanted to be 90% confident looking back. All right, and degrees of freedom are going to be equal to n minus 1. So in this case, my n was 30. So I end up with 29 degrees of freedom. All right, so I need to figure out what is T star for 90% confident and 29 degrees of freedom. So one way I could do that is using this handy dandy table. Okay, so using this handy dandy table, remember I want 90% confident and 29 degrees of freedom. So when I look where those intersect, and I get 1.699. So my T star would be 1.699. All right, now if I wanted to do that over here in StatKey, I would change my degrees of freedom to 29. I would click on two tail, put in 0.90 in that center box there, and I get 1.699. So same thing either way. So 1.699 is what I'm going to use. All right, so back here, my T star equals 1.699. Now I have everything I need. All I have to do is plug it all in and do the math, and we'll be all set. So X bar was 70. And we'll have plus and minus my T star, which is 1.699 times S, which was 12.4, divided by square root of 30. All right, so I'm going to work on this side over here. So 1.699. And then I'm going to take that 12.4 divided by the square root of 30. So 12.4 divided by square root of 30 gives me 2.2639. All right, what's the name for this quantity? This 2.2639 has a special name. What's the name for the 2.2639? Yes, this is the standard error, right? Okay, so now I'm going to multiply the standard error by my T star. So, and it's helpful if you can just leave numbers in your calculator. So that standard error number is already in my calculator. So now I'm just going to hit times 1.699, and then I get 3.846. All right, what's the special name for this 3.846? What do we call that? Margin of error, exactly. So this is going to be our margin of error. So now to construct my confidence interval, I'm going to take 70 minus 3.846, and then separately 70 plus 3.846, and that's going to give me the upper and lower bounds of my confidence interval. And well, maybe I have enough. Well, I'll put it over here on the side. I don't have a lot of space. So first I'm going to take 70 minus 3.846, which gives me 66.154. And then I'm going to take 70 plus 3.846, which gives me 73.846. So this is my confidence interval. All right, now I need to write a sentence interpreting this confidence interval, just the same way that we've been interpreting confidence intervals for several weeks now. So here's my confidence interval. I would say we are 90% confident that the mean number of fries and a medium order of French fries at McDonald's is between 66.15 and 70.85 fries. Oh, yeah, it should be 73. You're totally right. That is definitely a typo. 73.85 or 73.846. I'm not really sure why all of a sudden I went to using less decimals on this slide. All right, so that's how we're going to do a confidence interval. Now let's talk about how we're going to do a hypothesis test for one mean. And you recall that the general format for a test statistic is to take a statistic minus the null value divided by the standard error. So when we're looking at the test statistic for a test of one mean, same idea. We're going to have X bar, our sample statistic, minus mu naught, the value under the null hypothesis, divided by S over the square root of N. So that's standard error using S to approximate sigma. And I didn't have a separate slide to write down the hypotheses with. So the hypotheses, we'll write those over here. Okay, the null hypothesis is going to be that mu is equal to something. Okay, that's where this mu naught is. Whatever that something is our mu naught value. And then the alternative hypothesis is that mu is either going to be greater than, less than, or not equal to whatever that something is. So I'll put mu naught in there because that's where that mu naught value comes from. But when you do a problem, this is going to be an actual number. There's going to be a number that goes into there, not a symbol. All right, and our conditions for doing the hypothesis test are the same as the conditions for doing the confidence interval. So we want to have a simple random sample, and we want the population to be approximately normal, or our sample size is large. So again, we're going to do a plot of our sample data. If the sample data is reasonably symmetric with no extreme outliers, then we would consider that the population is probably normal. Or if that's all wonky, but our sample size is large, then we can still meet it with a large sample size. And our test statistic is also going to have degrees of freedom equal to n-1. All right, so when we're finding p-values, this is going to be very similar to how we found p-values using the normal distribution, but again, now we just have that one little extra piece to worry about with the degrees of freedom. So we're going to look at some examples here. We're going to do the first two together, and then I'm going to let you on your own to do the last three to test your skills. So again, we're going to go to stat key. And I'll start fresh here. So for the first one, I have a test statistic of 2.59. I have 6 degrees of freedom, and my alternative is a one-sided test. So I'm going to start by putting 6 in for my degrees of freedom. And I'm going to write what I'm doing over here in the corner in case you don't have that in front of you if you didn't print out that notes page. Okay, so T, my test statistic is 2.59. In this case, I have degrees of freedom equal to 6, and my alternative hypothesis was one-sided. All right, so I want to find the p-value. That's my goal here. Okay, so I already put in the degrees of freedom over here, 6, so that part's good. Now, Because my test is one-sided and my test statistic is positive, then I'm going to click on right tail. So in general, if your test statistic's positive, you're going to click on right tail, and if your test statistic is negative, you're going to click on left tail. So I clicked on right tail. Now I'm going to enter in the value of my test statistic, so that 2.59, and then this little floating box here is my p-value. So down here, this was my test statistic, and then floating box is the p-value. So there's a few more things to keep track of, but not too many. Really, once you enter the degrees of freedom, it's the same deal as when we were looking for p-values in the last couple of sections. So my p-value, 0.021. All right, let's look at the second one. So clear that one out. And I'll write these values over here. So for my second one, let's say that my test statistic is negative 3.25, and I have degrees of freedom equal to 23, and my alternative is two-sided. So this time I had not equals 2 in my alternative. And I still want to find the p-value. All right, so first thing that I'm going to do here, I'm going to click on Edit Parameters so that I can change my degrees of freedom to be 23. Okay, once I have my 23 degrees of freedom, since I have a two-sided test, I can click on two tail, and then I need to enter in the value of my test statistic. So my test statistic was negative 3.25. That would fall on the left side of my axis here. So I'm going to put it in the bottom left box, so negative 3.25. So if the test statistic is negative, put it on the left. And this is a two-sided test. So when I'm finding the p-value, then I need to double the floating box, or I'm essentially adding those two floating boxes together. So the p-value is going to be 2 times 0.0018, which is going to be 0.0036. So my p-value in this problem would be 0.0036. All right, any questions so far on what we're doing? Okay, so I'm going to go back to the presentation. We did number 1 and number 2 together. I want you guys to work on 3, 4, 5 and see what you get for those. Just have a little practice finding those p-values. Let's talk about the answers. So for number 3, the p-value should have gotten is 0.036. For number 4, the p-value was essentially 0. So it was like this really, really tiny number. If you rounded to 3 decimal places, then you end up with basically 0. And the last one, number 5, you end up with a p-value of 0.282. Let's just go look at these real quick in StatKey and review how to do them real quick again. So for number 3 had T of 1.85, degrees of freedom 39, and it was a one-sided test. So first I'm going to change my degrees of freedom to be 39. And it's a one-sided test, and my test statistic T was positive. So I'm going to click on right tail, and then I'm going to put that 1.85 down here in the bottom. So when I do that, then my floating box would be the p-value, which is the 0.036. Okay, for number 4, then this time we had 20 degrees of freedom. So I'm going to click on the degrees of freedom, change that to 20. It was a two-sided test. So I'm going to click on two tail, and my test statistic T was 5.87. So it was positive, so I'm going to put it in the right box down here on the bottom. 5.87. All right, and then I have to double the value in the floating box, or add the outer two floating boxes together. And here we get 0.000048. So that's super duper duper tiny. Even after I double it, rounded to 3, 4, even 5, 3 or 4 decimal places, it ends up being 0. So essentially 0 is our p-value. And then the last one, we had 14 degrees of freedom. So I put in my degrees of freedom. It was a one-sided test, and my test statistic was positive. So I'm going to click on right tail. And my test statistic was 0.59. So I put that in there. And then my floating box, the 0.282, would be my p-value. All right, so let's look now at actually doing a hypothesis test and see how that's going to work. So if you've seen a Chips Ahoy bag, then on the bag it says that there are 1,000 chips in every bag. And a group of Air Force cadets wanted to find out if this is true. So they bought bags of Chips Ahoy cookies from all over the country to see if they could test the claim. And then they hand counted the number of chips in 42 bags. So 42 was their sample size. And here was their data. So they got a mean of 1,261.6 chips, standard deviation 117.6, and they looked at 42 bags of cookies. All right, so first a couple questions. We'll answer these in our poll. All right, so can we use hypothesis testing to prove that there are 1,000 chips in every bag? All right, so the correct answer on this one is actually no, we can't. So it's a little bit of a trick question though. So if you're one of the majority that got this one wrong, you don't have to feel too bad. But remember that when we do hypothesis testing and statistical inference in general, it's always about a parameter, which is a number that describes the whole population. So we can't prove that there's 1,000 chips in every single bag, but we could look at whether there's more than 1,000 chips on average in every bag. Okay, so here's another one. Can we use hypothesis testing to prove that the average number of chips per bag is equal to 1,000? Right, another kind of tricky question here. The answer is still no. So remember that we can never prove that something is equal to something, right? So we never prove the null hypothesis. We're never able to prove statements of equality. We can just disprove statements of equality. So we're not going to be able to prove that the average number of chips per bag is 1,000, but can we use hypothesis testing to prove that the average number of chips per bag is more than 1,000? All right, hooray, almost everybody got this one right. So yes, so we can use a hypothesis test to prove that the average number of chips per bag is more than 1,000. We're not going to be able to prove that there's exactly 1,000 in every single bag, or that the average number of chips is equal to 1,000, but we can find statistically significant evidence, or we can attempt to find statistically significant evidence that there are more than 1,000 chips on average in each bag. So that's what we're going to do here. Okay, so we're going to do the hypothesis test. So first thing that we want to do is define our parameter. So remember, the symbol for our population parameter when we're dealing with a mean is going to be mu. And in this case, mu is going to be equal to the mean number of chips per Chips Ahoy bag. So mean number of chips per bag. All right, next, then we're going to write our hypotheses. Our hypotheses are always written about the population parameter, which in this case is mu. So for our null hypothesis, we said mu is going to be equal to something. And then the alternative hypothesis, it's either going to be greater than, less than, or not equal to that same something. So let's start with the null hypothesis. In the null hypothesis, what are we saying that mu is equal to? And it helps to think about what's the claim here. Yeah, remember the claim is 1,000 chips in every bag, so we're testing the claim that mu, or the average number of chips per bag anyway, is equal to 1,000. All right, now my alternative hypothesis is also going to have 1,000 as the number in it, but should I use greater than, less than, or not equal to here? Yeah, greater than, because keywords up here says greater than. So null hypothesis mu equals 1,000, alternative mu greater than 1,000. So this is a one-sided test. All right, next we're going to compute or identify, as the case may be, the sample statistic. And in this case, they told us what it was. So we know that X bar is equal to 1261.6. So we got that just from the data that they gave to us. All right, now we're ready to check the conditions, okay? And remember that we're looking to see if either the data is normally distributed, meaning that it's roughly symmetric with no extreme outliers, or that the sample size is large. As long as one of those things is true, then we meet the conditions. So here's a histogram of the data. Does the data look symmetric with no extreme outliers? Ish, right? Like I don't think it has any extreme outliers. It is a little bit on the skewed side, but is our sample size large, meaning greater than or equal to 30? Well, we sampled 42 bags, so we are greater than or equal to 30. So even if this, if we decided that this was skewed and didn't meet the condition that way, we do meet the condition with the sample size, the large sample size. So overall, we meet the conditions. Okay, so remember, only one of those things has to be true. As long as one of them's true, we meet the conditions. All right, so we met the conditions, and now we're ready to go ahead and compute the test statistic. So here's our test statistic formula. So we can just plug in everything. So X bar was 1261.6 minus mu naught. So remember, mu naught is the value of mu under the null hypothesis, which in this case was 1,000. We're going to divide that by S, which is 117.6 over the square root of 42. All right, so it's very important to remember order of operations here. Sometimes it can be useful to do the numerator first, then the denominator, then divide those out. So if I take 1261.6 minus 1,000, then I get 261.6 for my numerator. All right, and then if I take 117.6 divided by square root of 42, then that gives me 18.146 in the denominator. So now I divide those, so I get 261.6 divided by the 18.146, and I get 14.416. So this 14.416, this is what we call the test statistic. Okay, the test statistic, remember, that's just a standardized form of the sample statistic, and we use the test statistic to help us find the p-value. So one thing, like kind of a computational error that I see a lot here is, so people will do the numerator here. So they do the 1261.6 minus 1,000. So then you get the 261.6, right? And then they leave that number in their calculator and they say divided by 117.6 divided by square root of 42. Okay, so it ends up looking something like that. Okay, just like kind of a string of like divided bys. And the problem with that, so if you hit equals and you do that, then you get 0.343, which is clearly not the right number. The problem with that is that it's doing the wrong order of operation. So the division in the denominator has to take place before you take the numerator divided by the denominator, if that makes sense. So if you want to enter things in one long string in your calculator, then you have to put parentheses around the denominator so that it will do that division first before dividing the other way. So the order in the division makes a difference in this. So keep that in mind. Okay, so I have my test statistic. Now I'm ready to find my p-value. In order to find the p-value, then I first need to know degrees of freedom. So degrees of freedom is equal to n minus 1. So in this case, my degrees of freedom is equal to 42 minus 1, which is 41. So now I'm going to go over to stat key. I'm going to change my degrees of freedom to 41. And then I had a one-sided test and my test statistic was positive. So I'm going to click on right tail, and in the bottom box, I'm going to put what my test statistic was, which it was 14 point something, 14.416. All right, so I've got my test statistic down here. I entered the correct degrees of freedom. Then the floating box is my p-value, which my p-value is essentially 0 in this case. So really, 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 really unlikely to occur due to chance, in other words. All right, so back here, thinking about my p-value, there's like a little screenshot of what it looked like in stat key, and my p-value was essentially 0. So if my p-value is 0, 0 is really, really, really low, and we know that when p is low, then HO must go, right? So when we're writing our conclusion, we would say we reject the null hypothesis. We have super duper strong evidence that the mean number of chips per bag of Chips Ahoy cookies is greater than 1,000. All right, so while you're writing that down, I just want to point out something here. The test statistic and the t-star are totally independent of each other. Okay, so when you're doing a problem, you don't have to do both of those things, right? You can only do a confidence interval. You can only do a hypothesis test, which is what we did for both of the problems that we have here today. You could do both things. So in your homework, I'm typically going to have on the written homework, then I'm going to give you one data scenario and you're going to do both. You're going to do the hypothesis test and then you're also going to do the confidence interval. But what I see a lot is that students kind of get confused because there's so many things that have a T in them. Okay, so T with no star, okay, is the test statistic that we use to help us find the p-value in our hypothesis test. And T with a star is that critical value that we use to come up with our confidence interval. They are not the same thing, okay? They are different. So this number that you calculate here is not ever going to be used to construct a confidence interval. So when you're looking for t-star is not something that you compute. It's something that you know the confidence level, the degrees of freedom, and then you just find it on the chart or you figure it out in stat key, but it's not something that you compute. Okay, whereas T, our test statistic T, is something that we compute. Okay, we're going to compute this based on the information in our sample to come up with the number that then we're going to use to help us find the p-value. So you might want to make like a, I don't know, put a big star or something in your notes to remind yourself that T star and T are not the same thing. Okay, they're used completely differently. They're used independently of each other. So you don't need one to be able to get the other or vice versa. So hopefully maybe that'll help when you're working on your homework, because I very, very frequently see people that try to use this number as a t-star number in a confidence interval, which, like we said, is not the right thing to do.